Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so welcome everyone. Today we're very pleased to have Miran Kim visiting us from Seoul National University in Korea. Seoul National University is widely acknowledged to be one of the best universities in Korea. Miran will be speaking to us on a guide to applications of homomorphic encryption. Miran has done important work on maintaining and extending various libraries for homomorphic encryption and has won the edit distance contest in the Secure Genome Analysis competition last year. Thank you, Miran.
Yeah, thank you for introducing me and giving the opportunity to talk about my works. Today, I'd like to talk about the title, Guide to Applications of Homomorphic Encryption. I briefly explain the homomorphic encryption, and then I describe our basic arithmetics under homomorphic encryption, such as binary circuits and arithmetic circuits over the integers. And finally, I'll show you how to apply our primitive circuits to the real-world problems, such as private database query processing and secure DNA sequence analysis. Yeah, homomorphic encryption is an encryption function which permits computation of encrypted data without decryption. More precisely, it is an algebra structure preserving map between message space and plaintext space and ciphertext space. For example, we use a message space as a polynomial ring modulo integer p and cyclotomic polynomial. But we usually use a small subring z sub p, which is an integer from 0 to p minus 1. From this definition, it allows us to evaluate any arithmetic circuit homomorphically. And many homomorphic encryption systems have been suggested, such that Gentry's original scheme and as follows of words, such that DGHB10 and BGB12 and BLLN13 and so on. And in this talk, I focus on minimizing the number of sequential multiplication gates for a circuit, which is called depth. And the number of homomorphic multiplication can be considered as the computational complexity. This is because the error in the message grows exponentially or linearly with the multiplicative depth. And if the error is too large, then we cannot compute anymore. So the multiplicative depth is very important in homomorphic encryption. And now I explain our basic arithmetics under homomorphic encryption. Yeah. Suppose that we are given mu-bit integers, and then we can consider these four primitive circuits: equality, comparison, minimum, and addition. Equality circuit determines the equality of two inputs, and comparison circuit has one if x is strictly less than y, and minimum circuit outputs the minimum of two inputs, and the last addition circuit is just to add two numbers over z. And all the binary circuits are expressed as polynomials of degree mu, so they can be evaluated with a homomorphic encryption of depth log mu. And for the complexity, the equality requires mu's multiplication, and for the other circuit, their complexity are quadratic in the bit length mu. And however, they require many ciphertexts. For example, for only one mu-bit integer, we need mu ciphertext. Now consider these circuits over the integers. Suppose that we take a large message space, then the addition can be performed with only degree 1 circuits, but we have to choose P so as to perform these operations without overflowing in this message space. And we can revise the previous circuits using these facts. That plus XOR and cup and plus minus dot are arithmetic operations over integers. Then for one bits A and B, then we know that this property satisfy. So using this very simple observation, the primitive circuits can be computed efficiently with the same depth and same complexity. But however, there are still many ciphertexts because for equality and comparison circuit, we use the bitwise encoding, and each bit is considered as an element of large message space. On the other hand, we can revise the circuits using Fermat's-Little theorem. Let's recall Fermat's-Little theorem. For a prime p, x2 to the p minus 1 is 0 if and only if x is 0. So we can consider two important functions. The first one is the function chi sub k, which is a characteristic function of k, and it can be expressed using Fermat's-Little theorem. And then equality circuit, it can be seen as just chi sub 0. And chi sub k is a polynomial of degree p minus 1. So the depth is log p minus 1, about log p. And the complexity is also log p. And the another function is a step function, which has 1 if and only if x is from 0 to p minus 1 over 2. Then this step function can be expressed as a sum of chi sub k from 0 to p minus 1 over 2. So the comparison circuit and minimum circuit are expressed using this step function. And as you see, this step function also a polynomial of degree p minus 1. So the depth is about log p. And the complexity is, for computing chi sub k, we need log p multiplication. And we have p minus 1 over 2 chi sub k's. So the total complexity is big O p times log p. So the comparison and minimum circuit, they have the same complexity as follows.
Can I ask a question?
Mm-hmm.
So does this range, it's like a range query, right? It's like asking if it's in this range. Does it work if you change the endpoints of the range, or only works because it's 0 and p minus 1 over 2?
You mean if we change the range, then it'll be changed?
Will it still work? Can you still do it the same way?
Yeah, maybe it'll work, yeah.
So it's like a range query function.
Yes. And in the next slide, I will talk about if we change the range.
Okay.
Yeah. Mm-hmm. And we have a very nice advantage by using integer encodings such that there are not so many ciphertext. So for one mu-bit integers, we just have one ciphertext. And the next slide is if the domain is restricted to the intervals such that, for example, such x is from 0 to L or from p minus L to p minus 1, then the characteristic function and the step function can be expressed using Lagrange interpolation formula. So If we pre-compute m's of k's as constant values, then these are polynomials of degree 2 times L. So the total depth is about log 2 times L. So if the difference between two inputs is less than L, then equality comparison minimum circuit can be represented using this function, and they can be evaluated with a homomorphic encryption of depth log L, and the complexity is as follows. Yeah. In short, we have the following results given two mu-bit integers. If we use bitwise encoding, then the older circuit has depth log mu, but the number of ciphertext is very large. And in case of integer encoding, we first take p about 2 to the mu, so that the addition can be performed as just the modulo of addition in the message space. And first, if we use Fermat's little theorem, then the depth is mu, which is bigger than the one of bitwise encoding, but the number of ciphertext is very large, very small. And if the difference between two inputs is very small, then the depth can be reduced to log L, and it has also the small number of ciphertext. So you can choose bitwise encoding or integer encoding by the function that you want to evaluate. And we have another optimization such as single instruction multiple data technique called SIM technique. In short, we pack each messages into a single ciphertext, so we can perform an operation simultaneously for all the messages. More precisely, suppose that the cyclotomic polynomial factors mode p into a product of polynomial which are irreducible and has the same degree. Then the message space is isomorphic to a product of polynomial ring mode p and irreducible factors. So this is called plaintext slots, and we first embed our messages into plaintext slots and encode to the plaintext polynomial using Chinese remainder theorem, and then encrypt to the ciphertext. And we can also make extensive use of SIM techniques to move data across plaintext slots. Now I'll show how to apply our primitive circuits to the real problems. On 2011, there was a massive attempt to access the user account on Sony PlayStation. From this attacks, we've learned that we should encrypt sensitive information and store this data to protect them from such kind of data theft. And here is the query that we consider in our work. Suppose that we have a code for department and database table. Then we can consider this private search and compute query. Yeah, we first search the tuple who are in the research department and then aggregate their salaries. Yeah, there are several options. The first thing we can think about is searchable encryption, but they only support search operation, and it is weakly secure because that means like data distribution between plaintext and ciphertext domains. And the other option is using cryptosystems with layers of different encryption schemes, such as CryptoDB and Monomy. But they cannot support multiplication. So if you want to multiply, then the result value should be encrypted in advance or decrypt encrypted attributes. So we thought that homomorphic encryption schemes appear to perfectly perform such a database query with a single encryption scheme. The following picture illustrates our approach. We first suppose that a server holds an encrypted DB data consisting of tuples and attributes. Then let us denote T sub I bracket aj is the value of A sub j in a tuple T sub I. Then for the preparation step, the DB user prepares public key and secret key of homomorphic encryption and then publishes public key to a server and then encrypt their data and store in the encrypted database. For the submission of query step, a DB user first encrypts all the messages in a query queue under public key, say Q bar. And the message can be a keyword. And a server compiles Q bar into Q bar stars using processor by applying our techniques. Finally, a DB server evaluates over encrypted data and returns the encrypted result to a DB user. Let's think of our search and compute queries. We first check the equality of keyword type attribute and keyword. If they are the same, then it outputs 1, and otherwise it outputs 0. And then multiply numeric type attributes by this result, and then aggregate over numeric type attributes. If we encrypt all the messages in a bit-by-bit manner, then addition operation over encrypted data are very expensive despite our optimization, because addition includes very expensive carry operation, and carry operation require many multiplication. So our solution is as follows. First, we use integer message space. More precisely, keyword attributes. For keyword attributes, we use bitwise encoding because they are just used for search operation. And numeric type attributes are encoded by integer. So because they are used for compute operation, so using this encoding, we can reduce the depth of search and compute queries by big O log mu for mu-bit keyword type attributes. This is just for the depth of search operations. Yeah, and we also use the same technique in our experiment. We usually embed about 600 messages in one ciphertext and perform the query simultaneously for all the messages. And for the performance improvement, we represent each of numeric type attributes in the radix 2 to the omega. And the equation, we have the following equation. From this equation, we know that it suffices to compute just these red functions over the integers. So we choose a large plaintext modulus P in order to perform these operations without overflowing in the message space. And after evaluate this function and after decryption of this result, the user only has to shift and add. Here is our experiment result. We used the BGV scheme and H library by IBM. And we suppose the keyword type attributes 10 bits and numeric type attributes 30 bits. And for the equality search and sum query with 100 tuples, we took message space to the gist of 2D15, and we packed 600 messages in one ciphertext. And the running time is about 4 seconds. And the comparison circuit and sum query with 10 tuple, 100 tuple, then it took about 13 seconds. Now I want to talk about the secure genome analysis.
Before you go, could I ask some questions about the previous
Okay.
presentation? So how much difference is there between the search part and the sum part? So can you explain again, how do you do the search?
Yeah, so for the search operation, we use equality circuit and comparison circuit as I described above, and the sum is just add because we chose the large message space. So it is free operation, but for the search operation, it requires some. Yeah. So it is very important to accelerate the timing.
And here, capital N was the number of records?
Oh, yeah. You may assume that there are 100 people.
Mm-hmm.
Yeah. N is the number of people in the database.
Thank you.
Mm-hmm. Yeah. Many genome project displays genotype information in a public database. So we have to. So the genomic data has become public accessible, and one can recover physical characteristics from genomic data. So we want to use the potential of homomorphic encryption for secure genome data analysis. In our model, the data owner wants to store large amounts of data in the cloud, and many users may interact with the same data over time. In our solution, Cloud can handle all the interactions through computation on encrypted data, so it does not require further interaction from data owner. This could be more interesting in the situation of this picture. The data owner can be hospital or clinic, and the third party is patient. Then suppose the hospital would like to use the cloud services for analyzing a lot of patients' data. Then first generate public key and secret key, and then patients can upload their data directly with using public key, and then hospital request genomic queries to the cloud, and the cloud evaluate with public key and then return the encrypted results to the hospital. Then it can be decrypted by a secret key of hospital. Now, I'll explain the edit distance, which is a measure to quantify the similarity of two strings. In more detail, this can be the minimum number of edit operations, such that mismatch, insertion, and deletion, which is needed to transfer one string to the other string. For example, suppose that we have two strings, alpha and beta, and then we can make another strings by insertion of bar. Then the first same column is called match, and the last different column is called mismatch. And for the fourth column, alpha prime is needed to insertion of A in order to transfer into beta prime. So it is called insertion. And the fourth column, alpha prime, is needed to be deleted in order to transfer to beta prime. So it is called deletion, just called deletion. So in this case, the added operation is 2 mismatch and 1 insertion and 1 deletion. So it's 4, the total is 4. And it can be the candidate of added distance, because added distance is the minimum of this added operation. And here is the concrete Wagner-Fisher added distance algorithm. From 1 to 6, it's just the initialization step, and line 9 and 10 is the real computation step. We first check the character of inputs, they are the same or not, and then doing addition, and then computing minimum. Then we can create a matrix Dij, and by updating these entries. So the added distance is the last value d sub m n. Another aspect, if we consider the diagonal path, then we have to check the equality of the inputs, and if we move 1 unit down, it can be a deletion, and if we move 1 unit right, then it can be insertion. So in this case, we have to add 1 to the previous values. So I'd like to explain our encrypted added distance algorithm. Suppose that we are given 2 inputs, alpha and beta, over omega bit alphabet. That means that the character are omega bits. Then for line 9, we have to check the equality, and it is expressed using a equality circuit as described above, and we can add 1 by m steps in the x-axis, and add 1 by n steps in the y-axis. So the element of matrix is always less than m plus n minus 1. So it suffices to assume that d sub ij's are log m plus n minus 1 bits. So for this one round, we see that if we use bitwise encoding, then the total depth is depth of equality circuit over mu over omega plus depth of add circuit over mu bit plus depth of minimum circuit over mu bit. So the total depth is about 2 times log mu. And in case of integer encoding, the depth of addition is 0, but the depth of minimum circuit over mu bits is about mu. So we can conclude that bitwise encoding is better than integer encoding in our encrypted added distance algorithm. In short, given encryption of these kinds of values, then one can apply the above operations to compute the encryption of Dij with depth 2 times log mu, which is approximately big O log n plus m. And it is possible to d sub ij simultaneously when alpha plus j is a fixed value. So continuing this way, then we obtain the encryption of at a distance with homomorphic encryption of depths, these numbers. The first term is depth of one round. The second term is the number of rounds. However, it still requires two large depths. For example, if we compute at a distance with a DNA sequence of length 8, then we need a homomorphic encryption of depth 120. So it's impossible to evaluate. Yeah, maybe it took several days or several months. Yeah, it's impossible. Yeah, so we want to optimize the algorithm using block computation. First, divide the at a distance matrix into subblocks of size tau plus 1 and solve the at a distance problem in each block and compute each of them diagonally and update the entries. Then we know that the at a distance can be evaluated with only this value. The first term is depth of one block, and the second term is the number of rounds. Here is the result. And if tau is omega log m plus m, then the depth of one diagonal round can be big O tau. So the total depth can be reduced big O n plus m. Here is our experiment result with the same scheme and the same library. And for DNA sequences with length 8, we packed 682 messages into a one ciphertext. And so the total time is 5 hours, and the arithmetic time is about 27 seconds. Yeah. And now I'd like to introduce the Secure Genome Analysis competition on last year, which was sponsored by National Institutes of Health. And Genome Web and Nature report on this competition, and the teams were from Microsoft and IBM, Stanford, and MIT, and so on. And I also participate with the principal researcher, Christine, and we won a task of at a distance. For a task of DNA sequence comparison, suppose that two individual genomes were randomly selected from Personal Genom Project. And we want to compare two sequences with reference genome, which was known publicly. And the information of two genomes were provided as a variance Gall format file. Yeah, it is so. At first, it was so strange file. They have some concept. First, SNP. It is a single nucleotide polymorphism, and it is AGCT, as you know. And the ref is the reference basis. Yeah, here it is, reference basis. And alt is alternative non-reference string, which means the user's data. Yeah, alternative genome. And there is a SV type, which is a type of structure variant relative to the reference. For example, if non-reference doesn't have any SNPs, then then the SV type is deletion. And if the non-reference string have some SNPs, but while the reference doesn't have, then the SV type is insertion. Before we begin, we have something to do. The first thing is to create the data using the positions in the VCV files of two users. That is, server arranges the information and makes the merged list. And then we have to define we can define two encodings, E and F. The first encoding E tells us whether the genotype is missing or not in the list. And the second encoding F specifies the variant with respect to the reference. So if SV type is insertion or deletion, then it is just 0, and otherwise it is 1. And the user's string can be encoded as a binary string of length 15. As these rules, the first rule is each SNP is represented by 2 bits, as A is 0, 0, and G is 1, C is 10, and T is 11, and then concatenate with each other. And pad 1 at the end of string, because all the A string are 0 string, so we have to distinguish them. And pad zeros to make a 15-bit string. This is because we assume that it is enough to compare 7 strings between two users. So they are up to 14 bits by the first rule. And then we pad 1, so it's up to 15 bits. So it means all the user string can be seen as 15 binary string, say SI. And in case of missing genotype, that is E sub I is 0, then it is encoded just as 0 string.
Can I make a comment? So this length 15, that actually came from the data, right? That was because there could have been like up to 15 entries.
Yeah. Because in the file, some genotype has length 170. So but it's too large to compute over encrypted data, so we just cut. Yeah. So sometimes it outputs the different values, but it's correct in our experiment result.
What was 170 sometimes?
170 length. Yeah.
Like the insertion,
Oh no.
the alt thing?
Yeah. Old string. Yeah. In this exam, it just has one characteristic, but sometimes it has 180 SNPs, so it's too large. Yeah. So for
15 was just kind of an arbitrary
For performance of our experiment, I cut. And here is the Hamming distance algorithm. Suppose that Alice and Bob have genotypes over many SNPs, say xi and xi prime. And for a fixed genotype, define the Hamming distance at the locus as follows. First, the SV type is insertion or deletion. Then the Hamming, then we can think that they are different. They are perfectly different. So the Hamming distance is 0. And if one of them is missing, then one of them are missing, or the genotype are different, then the Hamming distance is 1, and otherwise it is 0. And then aggregate the Hamming distance at the locus. And here is our strategy. So first, Alice and Bob packed their data into plaintext slots respectively and encrypt using public key, and then evaluate the circuit for computing the Hamming distance at the locus in parallel. So if we want to bitwise encoding, then we evaluate the first circuit, and if we want to encode integer encoding, then we use the second circuit. And after evaluation of HI and decryption, then aggregate HIs. And here is a task that we want. Tang et al. Devised an approximate algorithm to compute the edit distance based from the reference sequences, but it was exact with 9%, but it has some advantage that it calculates based on the set difference metric, so it enables to parallel computation. And note that the full Wagner-Fisher edit distance algorithm, as described above, is computed in a recursive way, so the depth is too large.
What do you mean the depth is too large?
The depth in homomorphic encryption, the depth is the sequential multiplicative gate, the number of multiple gates. So, and it is very important to
You can't do depth more than about 20 for a homomorphic encryption. So that's what she means.
In terms of running time, that's
That's all she means. But
it depends. Yeah.
It just the performance just gets too bad.
Yeah. Mm. Yeah. And here is the approximate edit distance. For a fixed genotype, define the genotype length and edit distance as follows. For the genotype length, if the SV type is deletion, that means there is no SNPs in the user genome. Then take the length of reference, and otherwise otherwise she or her have the SNPs. So take the length of the old, and say D sub I, and the edit distance E sub I is 0 if and only if they are the same genotype, and otherwise take the maximum of the length and aggregate E sub I. And here is the evaluation circuit for bitwise encoding. For bitwise encoding, we use the first evaluation circuit, and for the integer scheme, we use the second circuits. And here is the implementation results with GH scheme and HE library by IBM, and BLLN scheme with arith library by Microsoft. We are given 2 DNA sequences with 5,000 genotypes. Then GH scheme took about 15 seconds for Hamming distance, and took about 40 seconds for edit distance. And BLLN scheme took 68 seconds for Hamming distance and 110 seconds for Hamming distance, for edit distance. And as I told, it took 27 seconds for evaluating just for 8 sequences. The the total the results are improving than the previous result.
Yeah, because the length here
Length is
5,000 instead
5,000.
of 8, so that's a huge improvement.
Oh yes, yes. 8 to 5,000. And we also provide a theory comparison between GHS scheme and BLLN scheme. They use the same plaintext space and ciphertext, but the main difference between two schemes is to encryption of messages. GHS scheme put the messages in the least significant bits of the ciphertext, but BLLN scheme put the messages in the higher bits of ciphertext. And GHS scheme use old cyclotomic polynomial, so there is no security reduction. But BLLN scheme uses the cyclotomic polynomial of degree powers of 2, so there is a security reduction to shortest vector problem. So BLLN scheme is more secure, than GHS. And we know that these two facts. The first thing is if M is multiplicative depth. If M is large, then the size of ciphertext modulus Q of BLLN scheme is larger than the one of GHS, but the bit size of ciphertext is less than GHS. And finally, I want to introduce my ongoing work, which is a floating point homomorphic encryption. And it was motivated by a project with Samsung. They want to compute the recommend system over encrypt data. Recommend system is recommend to the users that they want to see the movies or this kinds of thing. And so we thought that we first need approximate arithmetics. So we construct a concept of floating point homomorphic encryption. It outputs encryption of some most significant bits of addition and multiplication of messages, while the magnitude of significant is reduced. Significant is the part of floating point number that contains its significant digits. And our scheme supports more efficient encrypted floating point arithmetics than previous encryption schemes, which only supporting modulus operation. And we thought that our scheme can be applied to a large integer computation and multiplicative inverse. For example, with 80-bit security parameter, our implementation showed that our floating point homomorphic encryption takes 1.8 seconds to compute an encryption of 15-bit precision of multiplicative inverse given 20-bit precision of a number. This is the end. Thank you for your attention.
I have. Is there any way to convert between these representations, like from the bit to the integer, or maybe the floating point one, or are they like different domains completely?
Oh yeah, for bitwise encoding, we use just z sub 2 as a message space. But for large message for integer encoding, then we can use the z sub p for sufficient large p. They have the different plain text spaces.
Maybe there would be some way to do that using like bootstrapping. Like you would do bootstrapping, you would like change the parameters.
Oh yeah,
There might be some way to do it.
Yeah,
It would be very
yeah.
interesting to think about.
Yeah. As you know, bootstrapping requires many computation, and as far as know, the bootstrapping for integer scheme requires 6 levels. Yeah, so it's not cheap operation. Yeah, but in my works, I don't use bootstrapping. I just want to use the encryption just support small number of operations. So after with my parameters, after evaluating, we cannot compute anymore, but we have the correct answer.
You can do bootstrapping with only 6 levels?
Yeah.
What parameter sizes are you thinking?
With 18 security parameter. Yeah, it was not 80 security parameter.
Yeah, but what size for like Q and N and?
I don't know the exact parameter. It was just for the integer homomorphic encryption scheme, not ring LW scheme.
Approximate
Yeah.
GCD.
One of
That's
my
different.
friend is very interested is researching about the bootstrapping, and he has his work. Yeah, he said it requires 6 levels for bootstrapping in integer scheme, but I don't know the.
It's more.
Yeah,
for this.
it's more.
Yeah.
So what kind of techniques do you use in the floating point thing?
Can you go back one second?
Like, like the multiplicative inverse?
Oh yeah, multiplicative inverse, and we want to apply to approximate Taylor series. Yeah. In our scheme, frankly speaking, in our scheme, we cannot compute the exact value, but we can compute approximately to our desired result. So.
How many levels does that take? How many levels does that take to do? So, for example, the division.
For the
inverse.
division.
Like roughly, like how many? I mean, is it like 10, degree 10 or degree 20?
I don't remember the concrete parameters. I'll talk with you later. Yeah, I'll show our results. Yeah.
I wanted to ask a question. Oh, did you?
So in terms of your implementation, you report the runtimes in seconds or tens of seconds. Often. How much would it benefit from parallelization? So either multi-core or a cluster-based approach. Can we drive it down to milliseconds? Can we do that?
So you mean what is the advantage by the parallel computing?
Yeah. How far can we optimize this? What's the potential there?
Yeah. As far as I know, we can. Yeah, the total time is the same, but before we encryption, we encode several data in one plain text slot. Yeah, one messages. Yeah, I show my slide.
Yeah, so there's like several steps in doing this.
Sure.
And
Some of them I think would
are-
benefit from parallelism, but I'm not clear as to what the bottleneck would be.
Yeah, it depends on how many we embed in the slot.
Mm-hmm.
Yeah, so the total time is just divided by the number of the slots. Yeah, this is the emergence time, and we can compute the same operations over the many messages.
So your implementation is not SIMD based, or it is SIMD based?
Yeah, this is SIMD based. Yeah.
So the numbers you report are SIMD based.
Yeah.
Okay.
I mean,
so there's already a fair bit of vectorization happening.
Yeah.
Or some level.
I heard that. It is more correct that we call this batching technique.
Yeah, that's. I mean, it's a form of data parallelism, which has its upsides. So, okay, so this is interesting to find out. I mean, to realize. Yeah.
Yeah, it's interesting. There's like this parallelization like happening inside the algorithm. It's not that like.
But I mean, like we work with these things, right, in our group, and there are ways to push this beyond this. Like you started SIMD, but then you can push it further in a sense if you play your cards well.
Well, I think there's additional levels of parallelization that are not happening yet here. So one is, if you look even at the lower level of the FFT multiplications, the parallelization is really not being used there yet. There's another level on top of this that could be implemented, which is kind of expanding your capability by doing multiple CRT essentially on the plain text, and you can do that in parallel. So there's like at least 3 levels of different types of parallelization.
It sounds like there's a fair bit of potential.
Yeah, there really is.
Which is really quite nice to hear.
So I have a question. So, I mean, at a high level, a lot of what you're doing for the different applications and different tasks is examining these trade-offs between really the depth and the ciphertext size in many ways, because with the integer encoding, you have reduced the ciphertext size so dramatically. But for multiplication, like for comparison and quality checking, you're increasing the depth. And so there's this, kind of balancing act that you're doing for different applications, and which also affects the parallelization possibilities as well. But it's still an open question, kind of optimizing, for any given task. Here's a task. Optimizing this encoding choice, and these trade-offs. So I just wonder what you think about that, whether you have any ideas for kind of a general optimization.
In case of me, if I need many addition, then I usually take the integer encoding because the addition is free. But if I don't need to operate the addition operation, then I'll usually choose the bitwise encoding. So I think there is it depends on what you evaluate, and but someday we can we can do that. And we can consider the better circuits for equality and comparison. Yeah.
Do you think like the techniques you use could be like automated then?
Automated?
Like you showed several techniques for how to improve these sorted algorithms. Do you think like that logic that you obviously did by hand could be put into like a compiler or something? Is it general enough, do you think?
It's not general, I think. Yeah.
Looks tough.
Yeah.
At least partially.
Yeah.
Should be
And you can sort of imagine the compilers for some of these.
Could you say that again? I'm sorry.
Some of these, right, sort of recipes, quote unquote, right, you mentioned sort of all the time. It's compilers that encode those, making this process a little bit more automated. Right, I mean, as long as you can discover strategies to convert them into some form of automation. It's a long-term goal.
Yeah, not very.
Any other questions? Okay.